Now that we know how to take partial derivatives, we want to expand that knowledge to composition of functions because, of course, many functions that we're going to work with have not just one but two variables or more. So we have dependent variables, and they depend on two or more intermediate variables, which will in turn depend on one or more independent variables. So it's helpful to visualize this composition using a tree diagram. So I'll make a tree diagram as we go. So let's imagine sand slowly being released from a chute, and it's forming a cone-shaped pile. So if you have sand dripping out like in an hourglass, it's going to form a conical pile, like a cone. And that cone has a volume, right? So it has a certain amount of sand in it. Now the volume is dependent upon two things. It's dependent upon the height of the cone, and it's dependent upon, oh sorry, my height got weird there. So, and it's dependent upon the radius of the cone. So height and radius. And of course, they form a right angle. But there you have it. All right, so if I think about volume as my dependent variable, it's depending on two things, height and radius. But of course, height and radius are actually both dependent upon another variable because this is sand coming through a chute. So therefore, they're both dependent upon another variable, which is time. Time is passing. Now we use this theory a lot in Calculus 1 without actually kind of getting into what it is. It's this that allows us to do related rates. So this is the independent variable here. These are the intermediate variables. Intermediate, there we go. And this is the dependent variable up here. All right, lovely. So this is very similar to related rates from Calc 1. Matter of fact, it is related rates. We just don't teach it this way generally. I'm not entirely certain why, because maybe students would understand it a little bit better. But in Calculus 1, you basically have volume is related to height and radius, but things are passing over time, and so you introduce another variable, time, the independent variable, and work that way. Similarly, let's say a company manufactures a box of cereal, and the cost of the box depends upon, okay, well, all sorts of things. Oh, I don't know if I put these up here. Sorry. I should add these. It's height or time here, because how long the sand has been flowing, and the height depends on how long the sand has been flowing. So T becomes our intermediate variable. And then volume depends on radius and height up here. All right, sorry about that. Now back down to here. So we have a company manufactures boxes of cereal. The material cost of production depends on two things. It depends on the cost of the box, so box, and the cost of the cereal. Okay, but the cost of the box depends upon the length, the width, and the height, right? So length, width, height of your box. But so does the cereal, because how much cereal you're going to put into this box depends on the length, width, and height of that also. So let me just remind you, when you have a box for cereal, right, you have a length, you have a width, and you have a height. So height's over here, length's over here, width's over here. Oh, I used capital letters, so I better make this capital L. There you go. All right, so the cost of the box, the cost of the box of cereal. So let me put it for P for production cost. All right, so that depends on B, the box's costs, the cardboard and all of that, and C, the cereal you're putting inside of it. Now each of these depends on three things. Right, cost depends on length, width, and height, and so does the box. It's just that this is cardboard, length, width, and height, and this is how much space there is in the box to put cereal into it. So this is the dependent variable up here. These are the intermediate variables here. And then these are the independent down here. Okay, now that we see that multiple variables can be attached, both intermediate and independent variables, to a larger dependent variable, what does this mean for taking the derivative? The answer is if you want to find the rate of change or derivatives of the dependent variable with respect to independent variables, it's often more efficient to use a derivative rule for composition of multivariable functions instead of substituting and ending up in kind of a mess. What you'll do is essentially the chain rule. So let me remind everybody really quickly. The Calc 1 chain rule says if you want to take the derivative of y with respect to x, you take dy du times du dx, right? You introduce that intermediate variable, which in that case is u, and we use the letter u a lot for the same reasons that we use it for u substitution. It's kind of all the same thing. Okay, now how does that mean for us? Well, let's think about our volume of sand. Actually, I don't want to move that out of the way. So we had volume dependent on height and radius, and each of these was dependent on time. So if I want the derivative of volume with respect to time, right, this variable, what I'm going to use is these as my intermediate variables. So I'm going to take the height here. So I'm going to go from volume to height to time, kind of work my way that way. So I'm going to take the partial derivative of volume with respect to height, because there's two options there. I'll use delta times, well, height only has one variable below it, so it's dh dt, plus, and then I'll do it again for the other side. So volume goes to radius, radius goes to time. So it's delta v delta r, because I'm taking the derivative with respect to r, but there were two options for variables, so that's why I use delta here, times dr dt. Each of these is a separate chain rule. You're using chain rule right here, and you're using chain rule right here. Right? They are the same as the Calc 1 chain rule up above. That's just with deltas. Right? This gets you the overall chain rule for partial derivatives. This is how it works. And it really pays to have the tree diagram built, because then it makes it really obvious which way you have to go. All right, so let's look at the serial. The serial was the price or production cost is dependent on B and C, and each of these was dependent upon LWH, LWH. Okay, so the derivative of P with respect to, they want the derivative with respect to width, so I'm going to pick W. Now, why did I do delta here and I did D up here? Well, I did D up here because there's only one independent variable here, and that's time. Oops, I just wrote on my paper, time. Whereas down here, I have three independent variables. And so in that case, I'm using delta because it's a partial derivative then. Sorry, my T up here is bothering me. There we go. Okay, so I'm going to take the partial derivative of P with respect to B, and it's delta because there's two options, times, now down here, well, actually, let me go this way. I'm trying to go like that, right? So I'm taking the partial derivative of P with respect to B. I just want to color code it. Times the partial derivative of B with respect to W. Because there's more than one variable option here, I'm going to use deltas. Plus, right, and then now I'm going to go this way. I'm going to work my way down. So partial derivative of P with respect to C times the partial derivative of C with respect to W. And there you have it. So if you have the tree diagram figured out, you can just kind of circle the path you're going, and then those will be your derivatives. And there's just a notation note down here, which is when there's only one variable, we use d, such as dv dt or d dh dt, those kinds of things. Right here, we use dv dt dh dt because t was the only potential independent variable. When there's more than one variable possible, we use delta, such as d volume, right up here, dv dr. Delta V, delta H, those ones, or down here, all of them, because all of them had multiple options at every single level. So that's just a little notational note about when we use deltas and when we use Ds.